This is session 7 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton Fick. In sessions 5 and 6, we began an exploration of explanatory variables that are not discrete or dichotomous, where we have a large number of possible values of a particular explanatory variable. And so what we did in sessions 5 and session 6 is explored the wide range of situations in which using linearity seemed like a wise thing to do. In other words, fitting lines, using models that give us lines. There are a wide range of settings in which the linearity assumption, that is, that the rate of change, or that the log of the odds ratio varies linearly with some explanatory variable like age, and that we can express that linearity with a slope. Now, there are a wide range of ways in which epidemiologists and biostatisticians handle circumstances in which it is at least speculated and perhaps clear that the linearity assumption is not appropriate. And so now for session 7, we wish to explore the challenge of how to address the nonlinearity issue. Perhaps the most direct is by means of grouping, and that is taking an explanatory variable which has many values and placing the explanatory variable into groups that are mutually exclusive and exhaustive. So we'll look at that first. Then we'll look at the lowly parabola and how it can help us. Then we'll also look at a slight extension to the linearity assumption, and that is where the linearity is in pieces. And that will give us a second option that is often considered in studies. And then we'll look at some other issues, notably a methodology for nonlinearity that's gaining quite a bit of attention these days, and that is the whole area of splines, and in particular what is called a restricted cubic spline. And I think you'll find that quite interesting as well. All right. So we are now dealing with the circumstance in which we have some indication that these lines aren't doing the job. Now, that could come from a review of the literature that has already shown that linearity is not appropriate. There is a wide range of language that's used here. Sometimes people talk about U patterns or curvature. And we'd like to have a look at a number of these matters. It is also possible that the investigator assesses the linearity assumption by a number of different methods, and then on the basis of that assessment then is faced with using a method that includes for the possibility of nonlinearity. Okay, let's take a look at the grouping example, the grouping situation first. It has the illusion of being the easiest, but it becomes kind of complicated fairly quickly, and I think you'll see why. So we might then take our variable, and for my illustration, I'll suppose it's age, and take that actual value of age and place it into a set of mutually exclusive and exhaustive groups. So no overlap in the groups, and everybody in your study falls within at least one group. Okay, mutually exclusive and exhaustive. And now we'll suppose that there's k groups. Then you'll recall that it means that we will need k-1 indicators for the groups. And one of the groups will be the baseline group. If it's age, one might see a good case to be made that the youngest would be the baseline group, but there's lots of different circumstances here. All right, how about then if we have then strata? Now we've got, if we are looking at age and gender, age in k groups and gender in 2 groups, that means we've got 2k strata. Yikes. In other words, there will be 2k 2x2 tables. Well, we've already seen that, well, having enough information in each of these 2x2 tables can be problematic. That's the first thing. Determining by means of some sample size methods what minimum number one would need to explore such 2x2 tables is a big deal. It is possible, though. Okay, so we've decided we're going to at least give it a try. A stratified analysis with 2k tables, and we would then have its logistic regression equivalent, and we'll look at that as well. Okay, so there's, just to give us something concrete, or a little more concrete, let's suppose that we have 4 age groups. And that means there would be 8 age gender specific 2x2 tables. Notice here that the omnibus test for modification here would have 7 degrees of freedom, right? So a single test of modification would be, shall we say, lacking in specificity. Okay. Now, if we were somehow able to restrict our attention to the 4 age-specific 2x2 tables, then the modification test would have 3 degrees of freedom. And then there'd be 2 gender-specific tables and a crude table. So you can see that when we had strata where there were, say, 2 age groups, we had 9 2x2 tables. Well, as soon as we have 4 age groups, how many tables have we got? Well, we've got 8 plus 4 plus 2 plus 1. That's a lot. 15 tables now? Have I got that right? 12 plus 2 is 14. 15 2x2 tables in principle. Yikes. So that's already becoming probably prohibitive. On the other hand, it's not out of the question. Let's have a look at what the model would look like. You're thinking, some of the models we've looked at seem scary. Maybe this one does even more so. So suppose we did group the participants in the studies, and I've shown you a possible set of groupings. Notice they are mutually exclusive. This is something to be careful about. Like, how do you assign the individuals to the groups, and in particular when you're in the boundaries of the groups? Something to be clear about in your analysis. Okay. And this model with now, 16 regression coefficients, right? Well, that's coming from the fact that, remember how many tables there were? There were 8 age gender specific 2x2 tables, and hence 16 probabilities. There are 16 odds. Yikes. Okay. And as I mentioned, in this case, we could address from this particular model whether age modification is indeed modified by gender. And you can see that that would be also omnibus. It would be a 3 degree of freedom test. And if there's no evidence against this null hypothesis, then we could try again with a model that excludes those 3 terms. And then what does that take us to? That takes us to the situation in which we can address age modification, assume common to gender, gender modification, assume common to age, and then some possible further fitting depending on the results you get from this, right? And notice this is directly borrowing from the work we did in session 6. Okay. And there are many other, as soon as the model numbers, the number of parameters gets large, obviously the number of contingencies gets large too, right? But I think there's one issue that perhaps deserves some comment here, and that is the models themselves don't tell us about the nature of the log odds age relationship, right? This is not going to give us an indication of how the log odds varies with age. In particular, is there really evidence of nonlinearity? And so we have some issues here that are new and maybe problematic. However, I can tell you that there are instances in which investigators use this tables methodology, the stratified analysis and its logistic regression equivalent, as an interesting way to explore what's going on in a complicated study where the relationship between the log odds and age might be fairly elaborate and needs some careful consideration. All right, now let's go to the parabola, and hopefully you've all seen such curves. Some authors use the somewhat maybe oversimplified language of U-shape, right? But a parabola is a fairly specific U-shape. But on the other hand, it may be that the nonlinearity in your project can be managed by at least part of the arc of a parabola. Okay. And that the nonlinearity can be handled in a comparatively simple way with this parabola. Okay, well, maybe it's time for a little bit of review of something that you almost certainly saw maybe for some of you many years ago, but it's going to be important for us for interpretation. And it is the lowly or the simple, I don't know whether it's simple or not, but so-called completing the square. Well, there it is. Think of a function then that is a quadratic function. It is, in fact, such a function gives us the graph of a parabola. Yeah. And, in fact, if we look at a particular equation, we get what look like somewhat mysterious-looking numbers. Here, this number, here, this number here, and this number here that we might get, say, from a fit somehow. But in fact, this rather mysterious-looking equation can be written in a quite nice way, and that is using the completing the square methodology here. Why would I want to do that? Well, notice that when x here, what might be age, is 45, then this term is 0. We get 45 minus 45, so this term is 0, meaning that the function is minus 8. So if this was a logistic regression, we would be getting that the log of the odds in some scenario is minus 8. What can we also see from this is that this number here is, if it's not 0, is positive. That comes from the square here. All right? That means that minus 8 is the minimum. It's the smallest log odds that we can get, and it occurs for persons age 45. Okay. Let's look. That is a graph of that function. And notice we see its lowest value when the log odds is minus 8 at age 45, and then rises for those who are older than 45. And notice we get an exactly symmetrical curve. So it means that if I took this curve and folded it along the line x equals, or the vertical line log odds equals 45, If I fold it over, those two curves are the same. The left-hand side here would fit right on top of the right-hand side. So the parabola is a symmetrical curve. Now that can be something that some authors might have trouble with. It might be that the curve has a shallower decline on one side and then a steeper decline on the other, and a steeper rise on the other side. And the parabola won't do the job. On the other hand, this little piece of symmetry can be helpful and gives us a somewhat simplifying situation that might be helpful in some investigations. So a little bit of the technical part here, just to remind you that if we have a parabola, then it is, as we sometimes say, U-shaped. Okay? The bottom of the U is the minimum, which occurs when the age is minus b over 2a, and the value of that minimum is c minus b squared over 4a. That comes from that completing the square equation. So it means that if you have some, say, regression coefficient estimates, and suppose they were these numbers, it means you can determine where the minimum, in this case, the minimum value is, and at what value we get that minimum. Okay. Further, we can have an upside down U. Okay. And that occurs when the term in front of the squared term here is negative. In that case, we can see from this illustration here that this function with the negative coefficient here can be, using the completing the square, gives us this function. Then we get, when for persons age 65, we get that this term is 0, and then the function is minus 2, or perhaps the log odds in this situation. And now we can see that no matter what x is, if x is not 65, this number is positive, but this minus sign means that this number is declining, that this number is always negative, okay? Meaning that minus 2 is now the maximum value we can get. Okay. And so that's basically summarizing this. So the coefficients themselves look a little bit intimidating and are maybe hard to understand, but as soon as we complete the square, we can see what's going on. And here's a visual for that. Here in this instance, we're seeing if the study started with 20-year-olds, that it rises fairly, almost in a linear way, but then begins to level off. And then for those age 65, you can see that we reach the maximum. Now, whether or not the use of the arc of this parabola is helpful or not might be specific to those who are 65 and younger. It might be that we don't really believe that the curve begins to decline on this other side, for individuals larger than 65. Maybe that just doesn't fit things, but perhaps this study is such that most people are 65 or younger. Okay. So a little bit of a summary then. With parabolas, we get 3 characteristics that we'd like to understand. We get the curvature, that's the coefficient of the squared term. How curvy is it? The larger that value means the faster that the curve is changing in its shape, if I may. And further, we get where the minimum and or maximum occur and what the value of that minimum or maximum is. Okay, now, it is unwise to attempt to interpret the coefficients, as we'll see, of x or the perhaps constant term directly. We need those functions of those 3 characteristics to determine the curvature, to determine where the minimum or the maximum occurs and to determine the value at that minimum or maximum. Okay, now we're going to take some logistic regression equations that we've discussed, but now we're going to, we're going to make it even more complicated, perhaps you're thinking. Yikes, now we've got 12 terms. Yay. We've got the first 8 terms that involve the familiar piece we saw before, where we have the pieces that do not involve age, the parts that involve that are multiplied by the age, and the parts that are multiplied by a squared. Now, one little thing to remind you here is, since we now have parabolas, these things are no longer slopes, and these things are no longer simple intercepts. All of these equations are needed to construct where the minimum or the maximum is and where the curvature is at different particular circumstances. Let's look. So for this particular model, we get 4 parabolae. All right? We get a parabola for the unexposed women, and so on. The 4 different groups. Now, the equations are starting to get kind of complicated, but again, we can process this before we maybe throw up our hands in despair and think, I'll never understand this. In fact, well, it turns out you can, and it ain't so bad. Okay, let's take an example. For example, if we were to think about the unexposed women, then we can see that the curvature, how curvy the graph is captured by -8. And while these 2 numbers, which can be computed, and stated will do them for you if you'd like, determine where the minimum or the maximum is and what the value of that minimum and maximum is. Okay. So the coefficient in front of a squared here, beta 8 in this instance for the unexposed females, is telling us whether or not there's curvature. Okay? For, in this case, the unexposed females. You could see then that I would perhaps be interested in whether beta 8 is non-zero. In fact, I need to do that to ensure that these 2 numbers make sense, because both of them are divided by beta 8. Got to be careful about this. Both of these terms involve a division by beta 8. So what we've got to do is be careful here and ensure that this number, beta 8, is non-zero. And if it is 0, then we're back to the situation in which, at least for the unexposed females, that there's no nonlinearity, at least as captured by a parabola. Okay. Now, just as we had before, we can take that complicated equation with all those terms and also express it in terms of equations for the log odds ratio, and they're both parabola, and for the log of the ratio of the odds ratios, and it's a parabola too. In fact, it's a parabola if beta 11 is non-zero. So in fact, we can see that in order to determine if, for example, that the gender modification depends on age in a nonlinear way, we need to look at beta 11 first. In other words, this relationship between the log of the ratio of odds ratios will be nonlinear if beta 11 is non-zero. And as I said, this is basically reviewing that. If beta 11 is non-zero, then we've got, if I may, the most complicated of situations that might obtain, and that is that gender modification depends on age, and the nature of this modification is nonlinear. So now we're going to need visuals, again, the graphs that we spent some time with in sessions 5 and 6, in order to study the nature of this modification. Here's a little example. Suppose we carried out a fit and we got this particular equation. Okay? If so, we can determine that the ratio of the odds ratio on the logarithmic scale is parabolic. And we can see that for the 60-year-olds, this form of the gender modification's dependency on age reaches its maximum at age 60. Interesting situation. Might be something that's very important. The linearity assumption just might not be tenable. Maybe it might be okay for the young ages here, but you can see how it levels off if in fact this particular curve is an accurate description of the circumstances one is facing. Okay. We can see that the log of the ratio of odds ratios rises steadily from age 20 until about age 45, and then gradually levels off, and then is flat at age 60. Now, there are many other contingencies, just like we saw before. It could be that beta 11 is 0, but other terms are non-zero. And again, pictures are going to help you. Anytime you've got a circumstance that's starting to get a little bit intimidating and you're thinking, this is tough to understand, graphing what you've got, using Stata or your graphical software to display the curves that you fit. Vastly helpful in this instance. Okay, just briefly then, one more circumstance we might have is where we rule out all of the modification, and then we're looking at confounding. Okay, now notice with this, if we've ruled out the all of the forms of modification, and we're then wondering about confounding, well, it could be that we have an expression like this. Now notice that we've got beta 4 again in this illustration. That is the term that we wish to focus our attention on, and the extent to which beta 4 is capturing the disease exposure relationship. Okay? How does the relationship between the log odds of disease and exposure depend on the different ages and the two gender groups? Okay. So we might then explore, if in fact I do not have this term here, would I miss an important issue connected with the disease exposure relationship? In other words, it could be that the way in which I properly see confounding in this study is with the nonlinear relationship between the log odds of disease and age. In other words, this piece here becomes important in understanding that phenomenon. And there's issues of all kinds here. I'm only really illustrating some. In sessions 5 and 6, I've attempted to be a little more comprehensive in the number of circumstances one might see, but the truth is that in practice, in an actual investigation, you need to do the detective work. You need to address these issues and take the time to explore the implications of the models that you're considering. Okay. Something to keep in mind then, that if I'm in a situation where I have concern about confounding, then these are the situations we face. Okay? There's a whole complicated set of situations, and I'm not going to spend too much more time on this. But it turns out that we might have, even in circumstances where we're trying to address confounding, that curvature can be different for the males and the females, and that can be important in understanding the nature of confounding. Okay. The simple models might not do it, right? The models that assume linearity might not be adequate. Let's look at a little picture that might help. What have we got? Well, this is a somewhat complicated equation, but we've got, well, something involving exposure, and we've got the log odds of disease. What are we seeing here? What exactly is the scenario? Well, in this instance, exposure only shows up in this one place. Everything else in this model is about age and gender. And we've got this term that involves the nonlinear relationship between age and the log odds of disease. By the way, another point that I'll just mention for you here is I have centered age, if you can see that here, using age minus 45 for this display. And there's method in my choice of that. Okay. What do we get? We get now 4 curves. Let's have a look. Here is the curve for the unexposed women. The red curve is the the exposed women. And notice this vertical distance. That is that number, in this instance, because of how I've concocted this, it's 1. Okay? Notice that it is 1 for age 60 for the women, and it is 1 for age 30 for the women. The difference between red and blue for the 30-year-olds is the same as the difference between red and blue for the 60-year-olds, and that's for the women. But then I've got the same thing happening again with the men. It is orange minus green. And the vertical distance here is again 1. And 1 here. So what have we got? What we've got is a picture here that is enabling us to assess the disease exposure relationship. In this case, it's 1. It's the simple number 1. So the log odds ratio here, no matter what the gender, no matter what the age, that log odds ratio is always 1. Yeah. However, what have we done? Well, it could be that in order to see that the log odds ratio is equal to 1, I needed to include terms that capture what looks, at least here, to be pretty clear curvature, pretty clear nonlinearity. Now, understanding why it is that we're getting that form of nonlinearity would require some due diligence here. Okay? So notice the picture itself looks rather intimidating and complicated, doesn't it? Yeah, but in fact, it turns out that something fairly simple is going on as far as the disease exposure relationship is concerned. All right? All right. So that is an admittedly brief introduction to the description of nonlinearity with parabolas. And frankly, such a method for handling nonlinearity is still widely seen in health research projects. But there are other options. And another one that is just slightly more complicated than lines is where we have, in fact, two lines that are joined at a threshold. Okay. Now this looks a little bit complicated, but it is not too bad. Suppose we have two curves, two lines. One if x is below the threshold, and one if x is above the threshold. Two lines. The slope for those below the threshold, b1, the slope for those above the threshold, b2. If b1 is different from b2, that's saying that something involving the relationship between the outcome here and the explanatory variable is changing at some threshold. Next, it is very common with this sort of investigation to insist that the two lines are joined at that threshold. In other words, that the function remains what's called continuous. In other words, that we are able to not have to lift our pen if we're describing the relationship between the outcome and the explanatory variable. Let's take a look. If in fact the two lines must meet at some threshold, say t, that's saying that it must be true. That's saying that the function below the threshold and the function above the threshold must have the same value at that threshold. Well, that gives us a simple expression for this constant in this equation, a2, in terms of the other three. In other words, there's really only three things here, not four. If we're forcing the two lines to meet at the threshold, there's only three things that we need to have. Okay? We don't need a2 here. Okay, a little bit more technical stuff. Remember that the function has this form if x is below the threshold. And if we substitute for x greater than the threshold, we substitute this value here for a2 into the equation when x is greater than t, then we get this equation. This is a little bit intimidating, isn't it? Right? We're then seeing how, in fact, we're going to be using this. Okay? How the two things link up, how they connect. Nevertheless, it means that, in principle at least, we have the ability to describe the function where it's two lines joined at one value. Well, maybe not too surprisingly, it turns out that an indicator function that is 1 for being above the threshold and 0 below the threshold is probably the soundest way to set this up in order to carry out a fit. This isn't as bad as it might be looking. It's fairly easy to implement, and then the graphs that you see end up pretty nice, I think you'll agree. Okay. So using the indicator, we see that, in fact, what we have is a logistic regression equation now that involves three terms. Now, the interpretation of these terms will require some attention. Here is how we would set up this particular scenario here. In other words, if we fit this particular equation with x1 equal to this rather intimidating looking expression, and x2 equals this, well, we get what we want. We're going to get that If x is below the threshold, we get one line, and if x is above the threshold, we get the second line, and they're joined at the threshold. Okay, well, you're probably thinking again, oh no, Gordon, this is kind of tough. However, from a practical point of view, it means all you got to do is use, instead of, for example, a means of constructing this variable and a means of constructing this variable using generate. Not so hard. And again, here I'm going to show you a picture. Let's take, for example, this equation. Looks a bit complicated, but let's take a look at this equation first of all. First of all, if A is below the threshold of 55, then delta is 0, which means we do not have this piece and we do not have this piece. In other words, we get a line. If x is below if age is below the threshold, we get a line with this intercept and this slope, 3 over 35. On the other hand, if, in fact, age is over 55, then delta, the indicator, is 1. Okay? In which case, we get a change in the slope. Now we can see that instead of the slope being 3 over 35, it's going to be 3 over 35 minus 1 over 15. Let's have a look. Here is a graph of this admittedly complicated looking expression, but in fact, as soon as I instruct Stata to graph it for me, and then I start labeling things, I get what I need. I get a line that has positive slope here, right, until age 55, and then another line with a negative slope after age 55. This is called piecewise linear. So it's a line until age 55, and then it's a different line after age 55, but it's joined at that point, at age 55. And you can spend some time gaining some appreciation for what these expressions mean. Okay? So the two lines are joined. So it turns out that we can see that the log odds of disease, say, rises with age until age 55 and then declines after age 55. Okay? Now, it is certainly true that using this piecewise linear approach and that visual, you might be thinking, this is kind of unsatisfactory. All right, we've got this pointy bit at age 55, this point, this sharp change. Maybe unrealistic, you're thinking. Of course, it's not. We would have to say that near age 55, this is not working. Something else is going on. All right. Okay. So that's one issue. The second one is that in order to carry out this particular fit, I needed to specify the threshold. Now, it turns out there are advanced, more computationally intensive methods for handling the situation in which the threshold is left unspecified. We'll leave that aside for the time being. But it is arguably a weakness of this method that we need to specify the threshold in order to construct this particular fit. Okay. So we got the sharpness of the pointy bit at age 55 and the arbitrariness perhaps of the determination of the threshold, right? Okay, criticisms. Nevertheless, it turns out that we can consider the null hypothesis here that beta 2 is 0. And if we do so, then we're getting something that might be helpful to our understanding. And that is that in this instance, we're arguing that if beta 2 is 0, then this piecewise linear function is horizontal after age 55. This might be a much more tenable situation. That we think that the relationship between the log odds of disease and age rises, but then after some age, say 55, the log odds of disease doesn't get any worse. Okay? That might be a more tenable situation. It might be a more realistic situation. Right? Not a bad idea. And here's what the picture would look like in that case. Now, again, there's many other circumstances here. You could say it's still this pointy bit, still pointy, not quite as pointy, and there's still the selection of the threshold. Now, sometimes this type of pattern is thought to be helpful if, in fact, the parabola is really not doing the trick. It's really not doing things. Remember, the parabola would give us a curve that rises, hits a maximum, and then begins declining. And that might not be realistic either, that somehow the relationship between the log odds of disease and age begins to decline after some age. Many situations here. Okay. Now, as far as the implementation goes, here, you can see that all of the techniques that I described earlier in this session for parabolas can be addressed by replacing the terms a and a squared, right, taking the age and squaring it, and replacing a and a squared with these two terms, this thing and this thing. Again, notice I need to specify the threshold t, but if I'm okay with that, I get that instead of a model with a and a squared in it, I'm going to have a model that has a1 and a2 in it. And again, implementing this with Stata or R or any software system is not hard to do once you've decided you'd like to try that particular type of relationship. Very quickly, a brief illustration from a project that actually I was involved in some years back, and it had to do with gambling addiction. And I'll let you just read this, and so that I can get to the circumstance. But what we have is a circumstance in which we would like to try. This is failure here being recidivism. That is return to gambling. And we've recorded that log odds of failure here at a baseline time and then at 4 time periods. And we might then consider a piecewise linear curve, which we did at one stage in the presentation of this work. And if I do so, this is the phenomenon that we get. We get that in one group there is an improvement, but at the later time period, things appear to be about the same. So there's a lot involved in the interpretation of this picture, but the point being here is that we're describing two phenomena: an early change in the log odds of failure over the first time period, and then a more gradual change over the extended period. Okay? There's a fair bit more in play here. Other visuals here, we might see actually a decline in the log odds in the first time period, during an intervention with the intervention, and then unfortunately a rise in these two curves in the later time period, meaning that the impact of the intervention was fairly short in time. Okay. So we saw the parabola, and as I said, it is often considered. Well, there's a lot of literature it's some of it quite old, but a lot of literature around the use of more elaborate polynomials with higher degrees. Now, it turns out that in current times, one rarely sees these polynomials with, especially if in fact the polynomial is more than a cubic. And the reasons being that these curves you can really have some very odd shapes when m is greater than 3 in particular, and really no real basis for a realistic display of the relationship between the explanatory variable and the log odds. A big area that really should receive considerably more attention than I'm going to give it here is where one takes the explanatory variable and transforms it by some function, usually a nonlinear function. If it's a linear function, then we've already addressed what that has to do with changing the scale and changing the centering characteristics. But there are a whole range of other functions that are often considered in the analysis of an explanatory variable. Maybe one of the most common ones that's seen is to take the explanatory variable and compute its logarithm. But there are many other choices here. Big literature on this as well. There are more elaborate functions that can be considered here. For example, we could have that we wish to include some terms that involve like parabolas and maybe cubics, but also logarithms. Okay, or maybe even fractional powers. So where this number here was a square root, that's just a cube root, and so on. Powers, fractional powers, logarithms. Then we can have products of these things, a whole range of issues. For example, we can have, I'm just for illustration here, a fairly complex set of functions added linearly like this. And one very occasionally sees these in the literature, in part because, well, they've been tried in the past, and there was some success found, and so one sees their utility, and at least as a point of should we be trying this, and should this be given more attention. And here, this is one slide only, but on the very important, comparatively new area of the fitting of splines. And in particular, the particular type that's getting the most attention for sure in current research is the use of so-called restricted cubic splines. Okay, go back to the example I gave where we considered a piecewise linear situation. That's two lines joined at one place, and the place where they are joined has come to be called the knots. We can have piecewise linear functions with many other forms. We can have more than two join points, right? We can have much more general functions. We could have piecewise quadratics. We could have piecewise cubics. Well, it turns out that using the cubics and joining them at the knots can be done so in a way that makes the joining nice and smooth, so we lose the concern about the pointy bits, so that the cubics can be joined at these knots, and the curves you get then look like nice smooth curves without sharp edges. What has also come to be viewed as a very successful further consideration of splines is where we have them piecewise cubic, smooth at the joins or the knots, and the last two, both the front, the first interval and the last interval, are actually just lines. And there's some pretty sound reasons why one would want to do that. So we have so-called restricted cubic splines that are piecewise cubic, smooth at the knots, and linear at the ends. Widely seen now, getting a lot of attention, and with good reason. And there's a state of command called MK spline that provides for all of these situations. Okay, it's definitely time for an example. And let's consider one. This is a study of participants who have arthritis, and the participants are assigned one of two different treatments, and we'll call the treatments either treatment A or treatment B, coded 0 and 1. And then after an appropriate time, the participants were asked whether their symptoms improved. Improvement no, coded 0, and coded 1 for yes. So here we're modeling, in this case, the probability of improvement, or, for logistic regression, the log of the odds of improvement. Now further, for this particular investigation, there was some interest in the fact that the relationship between the log odds of an improvement and age might not be linear. This actually came from previous research. So the investigators then considered a model that addressed the treatment and the age, where treatment and age are included with this model with 6 terms, and we have allowed for the possibility that the relationship between the log odds of improvement and age is nonlinear. And like we saw earlier today, this model then gives us a log odds ratio, that is a parabola, and fitted values for that log odds ratio, that are parabolic. So here are the results. What have we got? Well, first of all, some of the basics here. In Stata, we generate the product of the two ages. We also generate the product of treatment and age, and the product of treatment and the square of age. That gives us all of the terms we need. We have the indicator for treatment and the age of the participant. Okay. This is the logistic regression that we would fit then. We're modeling this with the logit of improvement as a function of 6 terms, a constant, and then the 5 explanatory variables listed here. And in this instance, what we get is the coefficient of ta squared. It's negative. However, we can also see that it is, maybe you could say borderline, but it is statistically significant. Nevertheless, we can then construct the pieces that we need in order to understand the situation here. How do we interpret this number? Okay. What is this number here? So it's a small number, you might be thinking, but it's best not to focus your attention on the magnitudes here because of the fact that the age value, not centered in this instance, can be quite large when we square it. And so we're dealing with a whole range of issues. Okay, let's see if we cannot get a handle on what is actually going on here. We can see that this reflects the nature of this coefficient given here is telling us about the curvature for the individuals who are receiving the treatment coded 0. And then the sum of these two numbers, the sum of this number, 0.0026, and the minus 0.0065 are giving us the two curvatures in this instance. We've got the curvature for the person's coded treatment equals 0, and you can see that it is a parabola with a positive term, and the sum of these two numbers is actually negative. Okay, so for those coded t equals 1, we're going to have that the curvature is then down. So we've got a u, and then we've got an upside down u. Okay. As I mentioned earlier, we can use a function in Stata to compute the key ingredients in this instance. So this is the equation that's of primary interest here, right? This equation here, the log of the odds ratio involving the difference, and this term is telling us what this relationship looks like. Okay? And so I can compute if I may, we can compute the two pieces here where the curvature the difference in curvatures we saw was B5. So on the log odds ratio scale, the parabola has a value of B5, which is negative. So we know then that the graph of the log odds ratio will be a parabola facing down, upside down u. Further, we can compute where the maximum of that log odds ratio is. That turns out to be what the maximum of the log odds ratio is. It's 2.82. And the estimated age where that maximum of the log odds ratio is. And we can see that it's at approximately 47 years of age. And as I mentioned, these two numbers are displayed by these expressions, which we saw earlier, and we could have gotten Stata to compute them for us and give us standard errors and confidence limits. So there is the age at which the maximum occurs, and this is the value of that maximum. Okay? So we end up with two curves here. The first one that we had, by the way, was this parabola in the log odds ratio. Okay? But it can be of more value, by the way, to graph the two curves, right, using in this case, rather than the log odds ratio, which is this display, we can graph the two curves here. In other words, one for those who are exposed and one for those who are not exposed. Okay? That would be perhaps a bit more helpful in understanding. And you can follow through with the coefficients we get here, and I encourage you to do this. We can see that for the individuals who are receiving treatment 1, the so-called exposed, right, in this instance. Okay, so I mentioned this a little bit earlier. that for those coded t equals 0, or if I may, the unexposed, we get a parabola with a positive coefficient. And for those who are exposed, that's t equals 1, we get the difference between these two, which is negative. Okay, so that means that the log odds, in this case, going back, of improvement can be seen for the exposed. For those receiving treatment 1, the log odds of improvement, we can see, appears to rise with age and then decline. That's interesting, isn't it? So those people receiving the treatment coded 1, which was treatment B, there's a relationship with age, and it's the biggest benefit, if I may, might be happening for those around age 50 here. We saw where this maximum was. You can compute that. But that for whatever reason, the benefits of treatment B appear to decline for the younger people and the older people. The circumstance with treatment A, or in this case the unexposed, is a different situation, isn't it? See, the benefit appears to decline and then perhaps rise for those with the later ages. So what we're getting from this visual, this one perhaps the most interesting, is that the benefit or the difference between the log odds of improvement for those exposed and those unexposed is depending on age, and is dependent on age in a way that is not linear. There's certainly some suggestion that that's the case. And in fact, what we got from the graph of the estimated log odds ratio is that the biggest difference occurred at age 46 or age 47. The biggest difference between the log odds for those receiving treatment B and the log odds for those receiving treatment A was largest for those at about age 46. But then the difference appeared to decline for either the younger people or the larger people. And we can see that either from this display or we can see it here. Notice that apparently these two curves meet here at about maybe age 30, and here at about age 70. Now, whether or not that's really tenable to the edges of the ages is another complicated issue that we might want to entertain. All right, let's now have a look at a second example. This is from a study to understand prognoses, preferences, and outcomes and risks of treatment, which had the acronym SUPPORT. It was a prospective observational study of hospitalized patients. Okay. And what we've got is a number of different issues here that would be of some interest. For this particular brief discussion, we'll suppose that we're going to be considering in-hospital death as the outcome. We'll suppose that for this illustration that age is grouped. We have only two groups. We'll have those that are above age 62 and those that were below age 62. This is actually following the way in which one analysis was done. And we'll also look at this is the person's mean arterial blood pressure. Okay. And further, we're going to, for this illustration, we're going to use this data set to demonstrate constructing parabolas, constructing piecewise linear curves, and also to illustrate the use of restricted cubic splines. So we have some preliminaries. We generate some variables fairly clearly, and then we might begin by an analysis assuming that the relationship between the log odds of death here, the log odds of mortality, is a quadratic function of our variable B, mean arterial blood pressure. And if we did so, we might get the following logistic regression. So here we're wondering about whether or not the log of the odds of mortality is dependent on age, and maybe more crucially, there's some interest in whether or not blood pressure is involved. So what have we got? We've got two groups. We've got the group of people who are under 62 and over 62. So the blue curve here is the under 62 people, and here is the red curve, which is the over 62 people. Now you might be saying, well, that's an interesting display, more to show differing another type of circumstance with the use of parabolas. And you might be saying to me, Gordon, well, this term here is not statistically significant, blah, blah, blah. This is for illustration of the curves involved here. So you'd be quite right. Maybe there's no indication of a difference in nonlinearity between the young and the old groups here, but let's leave that aside for the moment and just look at the picture. If in fact we were to be interested in this sort of display, it would appear that for the younger people, that the relationship between the log of the odds of mortality and blood pressure, if anything, just declines slightly. But for the older group, it would appear that the blood pressure issue might be important, perhaps declining again for the lower blood pressures until some value, and then rising, where we might be thinking about hypertension, I guess, here in the older folk. Okay, so that's what we get from an analysis with in this case 2 parabolas, and we can repeat an analysis now. We can repeat an analysis here with piecewise linear curves. And I'm not going to go into the details of how you do that with Stata. One first uses the function mk spline, and then we use the results from mk spline to construct the explanatory variables that we're going to use in this analysis. So it looks a bit impenetrable here, but frankly, it's not that hard. And I would refer you to the help file on mk spline for the details of how to set this up. In any case, we get a rather daunting looking set of regression coefficients. This isn't really the point here. The real issue is, what are we getting? What sort of message are we getting? And if we were to try to understand the relationship between the log of the odds of mortality and this blood pressure measurement. And from this particular analysis, we get the following displays. And again, you might be saying to me, well, that's sort of not very helpful, is it? However, notice here, I'm using mk spline to construct 2 piecewise linear curves, and maybe you might argue this isn't terribly helpful. Again, more to the point here, just pointing out what you get from using mk spline for a simple piecewise linear analysis. And there's much more. Let's now illustrate this approach with a restricted cubic spline analysis. Again, we use MK-spline with a set of options, and again, the details are given in the help file for MK-spline, and this is set up nicely in Stata. It's also set up very nicely in R, for example. One can do so comparatively effortlessly, although it looks a little bit complicated. In any case, we then construct some variables based on what we got from MK-spline, and then we refit the logistic regression with all of these explanatory variables. Right? Maybe this doesn't come up too often, but by putting a star here, this means all of the variables that start with BRCS and all of the variables that start with ABRCS. A rather sneaky way to get all of the terms that you want. Then we get this long list of terms. Again, the actual regression coefficient estimates are rather daunting in their form. That's not the real issue here. What do we get? We get a different kind of visuals here, right? So now we get, with restricted cubic splines, curves that are linear at the edges in both the start and the end, and then are allowed to be cubic in between. And we get this potentially interesting phenomenon. Why it is that there is this bump might be worthy of some exploration. I'm not going to attempt to do so here. In any case, MK-spline and the use of restricted cubic splines or piecewise linear functions, pretty easy to do now with most software. And here's a little more about the background. I'm not going to, again, talk about this too much, but what is the background behind those piecewise linear curves? We get some functions that look a little bit, what's all that? But again, it's a sort of interesting picture. You know, there's a bit of an artist in me, I guess, isn't there? And I get another one. Okay, what is all this going on? This is for the restricted cubic splines. We get what are these curves that are used to build the restricted cubic splines?